Hello and welcome back to Differential Equations, section 5.5 on multiple eigenvalue solutions. We have seen the distinct eigenvalue solution with associated eigenvectors, and we have seen complex eigenvalue solution. And now we have this real repeated eigenvalue. And as we are going to see, in some cases, we are going to have the full set of independent eigenvectors. And in some cases, we will not have that. So we just need to talk about those two types of eigenvalues. So let's start with, well, let's write the theory, I guess. First, if my pen wants to work, there we go. So we have our good old system, the derivative of this one is going to give us the matrix times the vector of solutions, and we have the solutions given as C1 V1 E lambda 1 T plus C2 V2 E lambda 2 T plus dot 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 plus Cn Vn E to the lambda n T, which allows us to have any amount of unknown functions which is stored in the vector x. And we know that there was a characteristic equation from which we calculated the eigenvalues. So to get eigenvalues, we solved a minus lambda I equal to 0, right? And then to get eigenvectors, we solved a minus lambda I times V equals to 0. And when you get the eigenvalues, we can have a lambda to be real distinct, lambda can be complex, and lambda can be real repeated. We took care of these two, and today we are focusing on this one. Now, this breaks into two cases. It is going to break into a case where what we call multiplicity of K is complete. So complete. And in this case, complete, that means that we have a set of full set of independent eigenvectors, right? That's the way, right? And it's called defective when we have the set of dependent vectors. All right, so let's go and work on the complete. Now, just need to take a look the homework, see if I can figure out an example that would. Yeah, they're not separating them in the homework, so if I just pick any one of these, it might give me, well, whatever. So let's go and take a look at our example over here. So we have our vector of derivatives 9, 4, 0, negative 6, negative 1, 0, 6, 4, 3 times x, from where we know that our matrix A, right? So this is our matrix A, and then to find our lambdas, we subtract lambda on diagonals. So now we need the determinant, so that's going to be 9 minus lambda, 4 and 0, negative 6, negative 1 minus lambda and a 0, and then a 6, 4 and 3 minus lambda. Now we have 9 minus lambda times negative 1 minus lambda, 3 minus lambda, minus 0. Good. Then minus 4. And then you have negative 6 times 3 minus lambda, minus 0. And then plus 0 for the last one. That's great. So this gives us what? This gives us, we have to multiply all of these. So that's going to be 9 minus lambda times, this is going to be a lambda. Today the software decides to move and come on, stop moving. So lambda squared plus 2 lambda, right? This is going to give me plus 1 lambda minus 3 minus 2 lambda, and then minus 3. And then in this one I have 24 times 3, so plus and minus 24 lambda equals to 0. 24 times 3, so that's 72. All right. So now we need to FOIL all of this mess. Multiply by negative lambda first, negative lambda cubed plus 2 lambda squared plus 3 lambda, and now by 9 plus 9 lambda squared minus 18 lambda minus 27 plus 72 minus 24 lambda equals 0. A little bit of a mess over here to solve all of this. And that's going to give us, okay, negative lambda cubed plus 11 lambda squared, and then minus, this is, what do I have? I have a 3 minus 18 minus 24. I think those are all single lambdas, right? Okay, so that will make this into a 15, and then that's a 39 lambda. And I think have 72 minus 27. I don't have anything else. 5, and then still 1, that's a 6, a 4, 45. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . But they don't factor. I have, this should factor somehow. Let's see, 9 minus lambda, you know what? Let's see. I'm done with this algebra so 9 minus x, I'm just going to use software to simplify. This is too much. 3 minus x, and then minus 4, negative 6 times 3 minus x. There we go. Let's see what it's going to give. Negative x squared plus 11x squared. I got it right. I got it right. Okay, so now I'm going to type factor this expression. So when I type in factor, then we get, we get negative lambda plus 5, no, minus 5, and x lambda minus 3 squared equal to 0. So lambda is 5 and lambda is 3 with multiplicity 2. That's the repeated one. This is why we're here. All right, now question is, how do we solve this? So I did this correctly, apparently, and I thought I didn't because I wanted to do factoring by grouping and do all of these cute things that we know from algebra to factor this. Well, if it doesn't work nicely that way, that means that you have to use those possible rational zeros from pre-calculus 1. That's been like 4 years for some of you, 3 years, where you take the factors of 45 and then you use those numbers to check. And it's just, if you go into, I believe, 2.5 in my pre-calculus 1 lecture, you know what to do to factor this using those methods. So now, this is old and this is new. So this is what we are looking at for today. And what I'm going to do here is, well, we have to do both of them so we can have the complete solution. So we have 9 minus 5, 4, 0. Then we have negative 6, negative 1 minus 5, 0, 6, 4, and 3 minus 5. That needs to be multiplied by ABC vector to give us 0, 0, 0. So this is for lambda equals 5. All right, so the matrix is 4, 4, 0, then negative 6, negative 6, 0, and 6, 4, negative 2 times ABC to give us 0, 0, 0. Now, this means 4a plus 4b equals to 0 when you multiply the row and the column vector. Then we have negative 6a minus 6b to give us another 0. And finally, 6a plus 4b minus 2c to give us 0. So from the first row, we can pick a to be 1 and b to be negative 1. That will satisfy the second row as well. And we pick those because, 4 minus 4 is 0, and negative 6 plus 6 is 0. So we pick those values. Now, can you pick 2 and negative 2? Sure, right? If you want e and negative e, go ahead. So now we have these, and then we plug those in here to get c. So that's 6 minus 4 equals to 2c. So c equals to 1. And lambda 1 equals to 5. Produce the vector v1, 1, negative 1, 1. So that's our first eigenvector. Now we go to lambda 2 equals lambda 3 equals, what was it? 3. And we do the same thing. We have to subtract 3. So that's, what was my matrix? All the way up here. 9 minus 3. That's a 6. Was that a 4 and a 0? And I know there was a 0 here and negative 6 over here. Yep. Then we have a 6 and a 4. All right. And now I just need to subtract 3 on diagonals. Negative 4 and 0. Negative 4 and a 0. There we go. Times a, b, c. And then 0, 0, 0. So now my values here are 6a plus 4b equal to 0. Negative 6a minus 4b equals to 0. And then again 6, 4, right? 6a plus 4b equals 0, which is the same as 1. So now you pick the values on the first, right? Well, we can divide by 2 first to create 3a plus 2b equal to 0, right? And now you can pick values, and you can pick values so that you make them equal to 0. So you can pick a to be 2 and b to be negative 3. That's okay, right? Because that will definitely make you 0. So you pick literally anything that will make it a 0. And then the question is, what is the c, right? Because you're supposed to multiply by c and get the value. Well, to get a value for c, well, we don't have an equation that will give us c, right? So you can pick c to be 0. You can pick c to be anything, but c equals 0. So no equation to solve for c, pick c equals 0. And now we have our vector v2, which will be 2, negative 3, 0. But we can pick more vectors from here, right? Because you can also pick a trivial case of A plus B equal to, so okay, you are not allowed to have a vector 0, 0, 0. You are not allowed to have those vectors here because the vector 0, 0, 0 is a zero vector, which is just the origin, right? So you will not have a solution if you pick a 0, 0 vector. But for this equation here, another solution that we never picked before, A equals 0, B equals 0. This is new now, right? This over here is technically old. All right, that's technically old. We never had a situation where we had to pick the third variable like this, but if we did more 3x3 cases, you would run into it. Now, what we never did is we never picked A and B to be 0, because that would lead to C being a 0 and that solution was not allowed. It's called a trivial solution. So we have A equals 0, B equals 0, and then you pick a non-zero number for C. Because, again, not allowed to have 0, 0, 0. So pick C equals to whatever value, 1, 2, 3, 7, negative 30. So pick C1, right? And that gives us V3, 0, 0, 1. Would that work on top? Sure it would, right? Because it's 0 times 1 for C. So we have, technically our equation is 6A plus 4B plus 0 times C equals 0. So plug any of these vectors, right? If you plug in 2, negative 3, 0, plug in 2, negative 3, and 0. You get 12 minus 12 plus 0 is 0. So that vector is good. Plug in 0, 0, 1. That's 0 plus 0 plus 0 equals 0, right? So you are not allowed to have a 0, 0, 0 vector, but you can have any other vector, right? So now that we have our 3 eigenvalues and distinct eigenvectors, because these vectors are not linearly dependent, right? They're linearly independent. You can write your solution x of t, right, using these values. And remember what it is, what that is. C1 times the first vector, which was 1 and negative 1, 1, times e to the first lambda was, I believe, 5t. Was it 5, the first eigenvalue? Yep. And now we have 3's. Okay. So plus C2, my vector was 2, negative 3, 0, e to the 3t, plus C3, 0, 0, 1, e to the 3t. And if you want, you can write out the solutions, right, line by line. This is the answer. This is the answer. And we have 3, x1, x2, x3, right? Just read line 1, line 2, line 3. And as you can see, for the repeated lambda, in this case, we did not use multiply by t, because we had distinct, linearly independent eigenvectors. Therefore, there was no need to multiply by t. Now, for our second example, when we deal with defective eigenvalues, we are going to run into that. Defective eigenvalues. We are going to deal with that. So now let's take a look. For the defective eigenvalues, I am going to use A equals 1 and negative 3, 3 and 7, right? That's well, let's write a nicely equation, right? So that's going to be dx dt equals, there we go. To calculate lambdas, we know what to do. 1 minus lambda, negative 3, 3, 7 minus lambda needs to equal to 0. So that's going to be 1 minus lambda. We beat this one to death so far. And then plus 9 was to 0. That's lambda squared. Then we have minus 1. And then minus 7 is minus 8 lambda. Plus 7 plus 9. Lambda squared minus 8 lambda plus, that's 16 right there, equal to 0. And as you can see, this is lambda minus 4 squared equals 0 when you do square root of the first sine with the second square root of the third. And we get lambda equals to 4 with multiplicity 2. So we only have one lambda with multiplicity 2. So we find our, so now to find the vector, we take our matrix, subtract 4, so that's going to give us negative 3, and then negative 3, and 3, and that's 7 minus 4, 3. There we go, perfect. Times AB to give us 0, 0. So that's what we have. And now you can just pick any of these. You don't, right? Because they're absolutely the same. They're linearly dependent. As you can see, the one is times negative 1, right? So we have 3a plus 3b equal to 0. And from there, we can only get the vector negative 1, 1. Or 1, negative 1, whatever way you wanna write this. There are no other options for a vector. Every other vector that you write is going to be linearly dependent there, right? So we don't have, so this is called something that's defective, right? Because you cannot come up with another vector like we did in a past, right? And in this case, right, we have less equations than what we have variables to find, right? In this case, so we say that, right, I mean, 0, 0 would solve, but we can't use 0, 0 as a solution. Remember, you're not allowed to have vector of all zeros. So whether you picked negative 1, 1 or 1 and negative 1, right, yeah, we are stuck there. So what I must do is I just write out the solution for this. But see, I have my x1 solution to be c1 and my 1, 1, and then e to the, was it a 4? 4? Yeah, 4. 4t. So that's my solution. And we need to find another vector now to solve the problem. And in this case, the second vector. So let's see. What would be the best way now? So I have negative 1, 1. So this is my first solution. My second solution has to be dependent on the v1 and the v2, but I need to find the v2 first. Aha. So now we solve A minus, that's your lambda, I squared. So in our case, that's -3, -3, 3, 3, and -3, -3, 3, 3. That's over there 4 repeated root, in our case repeated lambda. And now what do I get? I get, when I do the multiplication, we get the row and the column. So that's going to be 9 minus 9. This is 9 minus 9. This is -9 plus 9. -9 plus 9. That's a basic matrix multiplication we did. We end up with a 0, 0, 0, 0 matrix. Alright, so now we use 0, 0, 0, 0 matrix times A and B to get 0, 0. And you can literally pick whatever you want because everything will satisfy. So let me write it this way. Any V equals AB, you pick, will work. Do not pick 0, 0. Do not pick 0, 0. So pick easiest one, 1, 0. Pick the easiest one. Very nicely. V2 equal 1, 0. There we go. Cool. So now that I have V2, we can go and create our matrix. So for x2 solution, so x2 is going to be v1 times t plus v2, and this is where repeated times t kicks in. E to the 4t, right? That's what we need. So now what do we have? My v1 vector was it 1, -1 or -1, 1? -1, 1. Stop flying. -1, 1 times t plus, and then v2 is 1, 0, and all of that times e to the 4t. And there it is. So now you can come up with the general solution xt, which is c1x1 plus c2x2, plugging those two values in, and we're done. Oh, what a mess. So that's it for this particular lecture. Now let's take a look at another example from homework. They do have mechanical problem where they have two masses and then they have a spring and a dashpot in between. They have 6 equations in between them, which is nice. Reduced down to 4 equations in a matrix. You can read that one. No way I'm going to do a four example here, take 2 hours. They skipped a lot of steps, but you can kill a lot of time reading that example. It's really cool. All right, so let's just pick one of these problems, try to go through it and call it a day, I guess. I mean, you are calling it a day if you're not going to study. I have to go. Great exams. So 1, negative 2, 2. 0, negative 2, 3, 0, negative 3, 4, x. So let's see, this is problem number 16 in the homework. I have no clue whether it's defective or complete. We'll see when we get there. So what should I do? Well, we're going to start by figuring out lambdas first, because we need to know that we have repeated lambda. So we're going to have 1 minus lambda, and then negative 2, 2, and then 0, negative 2 minus lambda, 3, 0, negative 3 minus lambda, no, lies, negative 3, and 4 minus lambda, much better. And that needs to be, I multiply the diagonal, and then plus 9, and then the other two are zeros. Nice. So we have 1 minus lambda, negative 2 minus lambda times 4 minus lambda, and then plus 9, and then close the parenthesis. Maybe I should let's use the higher order parentheses so you know that this has to be done first before you hit that with 1 minus lambda. That needs to be equal to 0. So I have 1 minus lambda, and these big parentheses now are going to be multiply everything. So I have negative 8. And then I have 2 lambda minus 4 lambda plus 2 lambda plus lambda squared. And then I have plus 9. And then I have 1 minus lambda. And this becomes lambda squared plus 2 lambda plus 1 equal to 0. And I have 1 minus lambda. And now, instead of multiplying and everything, look what I can do. Lambda plus 1 squared equal to 0. So I get lambda equals 1. And lambda equals negative 1 with multiplicity 2. So I have repeated lambda on lambda. So you can call this lambda 1, and this is your lambda 2. All right, so now lambda 1 calculation. Lambda 1 calculation is going to give us the matrix 0, 0, 0, negative 2, negative 3, negative 3, and 2, 3, 3, right? Times A, B, C equals to 0, 0, 0. Pick any of these rows. You can pick the last row. That's 2A plus 3B plus 3C equal to 0. And now we're looking for vectors, right? So what vector would make this? Now remember, this is a distinct one, so we just need to find one vector and we're good to go. So you can pick 0, 1, negative 1 would work, right? 0, 1, negative 1. You can literally pick anything as long as you are making everything to add to 0, right? So if you want to pick negative 3, 2, 0, that will work as well. negative 2 lambda back in calculations. Negative 2 lambda, we have, is it negative 2 lambda? I have negative 8. This times this is plus 4 lambda. And then minus this times this is going to give me negative 2 lambda. And this times this is giving me plus 4 lambda. So together it's plus 2 lambda when you combine them. Right? I think this is good. Negative and negative is positive. Wait, did I have my... No, I have my signs wrong. Negative 2 times negative lambda is positive 2 lambda. And that's negative 4... Ah. So that's a negative there. And if that's a negative, then this is a negative. Ooh, that works even better. I only have 1 lambda now. This is equal to negative lambda minus 1 cubed, which gives us only 1 lambda now with the multiplicity 3. Oh, this is even better. Thank you for fixing my arithmetic. I was just checking if you are... I was just checking if you guys are paying attention, obviously, as always. So I have lambda equals to 1 with multiplicity 3. Lambda equals 1 with multiplicity 3. By the way, this one, right, in algebra, if you have a minus b, that's equal to negative b minus a. So if you just flip it to be lambda, that's what spits this minus out. But this minus doesn't change. So... okay, cool. There's way too much signs over here and things. Alright, so lambda equals 1, multiplicity 3. So we're supposed to find 3 vectors. And now let's see if it's going to be defective or... So what do we get? 1 minus 1 is 0. So we get 0, 0, 0. Subtract 1, we get negative 2, negative 3, negative 3. And then 2, 3, 3. Times A, B, C to give us 0, 0, 0. Nice. All right. So all I need to do is to, again, if you row reduce this, those of you from linear algebra, you know what row reduce means. You can put any row you want anywhere. This would actually be 2, 3, 3, 0, 0, 0, 0, 0, 0, and then A, B, C, and then 0, 0, 0. From where we can only pick one equation, and we can try and find vectors. Right? So now you have 2 rows of zeros. Now, let's go back and take a look at this. There's a row of zeros there. And go back here. There's a row, 2 rows of zeros here. Right? So, this is what we have all the time. What are my vectors? Well, the one vector that we can find here is definitely, we can go with 0, 1, -1. So 0, 1, and -1 could be the vector. Let's try it. That's a 0 plus 3 minus 3 equals to 0. Now, any multiplicity of this vector doesn't count. You have to find, if you can, independent vectors. You have to find independent vectors. So you cannot use 0, 2, -2, because that's dependent. That's just going to be 2 times v1, right? So you can't use that one. Or any constant multiple of this vector. Any constant multiple on this vector would be dependent. Question is, can you find a vector that it's independent of this one? And the answer in this case is yes, right? Because think of it, you can pick b to be 0, let's say, and then you can use 3 and -2, right? That's going to be independent from v1 because you cannot multiply v1 by a number to get v2. So you have to play with these things, right? You play with A, B, C, trying to find the values that would work. How about v3? That v is terrible. The row reducing. Oh, I just add. I'm not sure for some reason tablet is really overheated now. I'm only using it an hour. Usually when it starts blinking like this and jumping and twitching is when it overheats. But that's usually at the end of the day. Not for your class, but right now, whatever. So how does the row reducing works? All I did is I added these two equations and I listed the third equation first. That's all. I did not do any row reducing here. You can't row reduce this matrix anyway. All right, so let's go back to this. So pick the first vector as 0, 1, -1, and then pick the second one when b is 0. And now I'm just going to pick c to be 0. And pick, let's say, 3 and -2. And you have your 3 independent vectors. So we were able to do this, which is why we did it this way, right? You were able to find vectors that are linearly independent, and that now creates our solution. Let's go here. X of t is going to be c1 times the first vector 0, 1, -1 times e to the t plus c2 vector 3, 0, -2 e to the t plus c3 vector 3, -2, 0 e to the t. And that's the solution. Right? If you want the exploded form, I call it the exploded form. If you want to list all 3, right, you will have x1 of t equals to, now see there is a 0 there, right? So there will be no c1 term, you will just have c2 and c3 terms. And then for the x2 you would not have c2, and for the x3 you would not have c3. This could be your mechanical problem with the dashpot, right? When you have a dashpot in, this could be a mechanical system, and with the solutions that are actually, there. So there we go. We have 3 examples. 2 of them were 3 by 3. 1 of them was 2 by 2. Your homework on page 347, I believe. Yes. We'll have 22 problems to enjoy. Out of those 22 problems, 6 are 2 by 2, and the rest are 3 by 3. And they also give you a lot of annoying problems. If you go to problem 32, they give you 5 by 5 to enjoy. There are a couple of 4 by 4s. On the exam, you are either expecting a problem just like 2 by 2, obviously, or 3 by 3 that was exactly like this. So 3 by 3 that will have a row of zeros on top. Because remember, row zeros, 2 zeros on top eliminated those 2 large calculations that we had to do when we do the determinant of 3 by 3, right? Because 3 by 3 determinant has to be reduced to 3 2 by 2s. And because those were zeros, the second 2 2 by 2s determinants were eliminated in calculation. So for exam, it's either going to be a 3 by 3 case that will have 2 zeros in the first row, or it is going to be 2 by 2 case, right? So you will have something like that to show the repeated. And, a problem like this should not take longer than, 5 minutes or so to solve if you know what you're doing. Obviously, if you are trying to make stuff up as you go and look for the example and so on, yeah, good luck with that. But the biggest issue over here, obviously, is factoring and, trying to get the stuff. So the exam has to be next week, next weekend, right? We don't have any other choice. Let me see, what else do we have? So we're done with this. How much of this stuff do we actually need? So we can survive with just going one more lecture with a 5-6 matrix exponential. We don't have to worry for non-homogeneous systems. That's when you implement variation of parameters and undetermined coefficients within these matrix solutions. We can even those are good problems, obviously, because a lot of systems are driven by external forcing. That's for application, right? But then, you can also read that. So I would say let's finish on Monday on 5-6, because we are really short on time. Finish on Monday. Probably do review on Wednesday. And then Friday start Laplace chapter 7, so that we can go into, start Laplace and do 7-1. 7-1 is short, so 7-1, 7-2, and then the next Monday finish 7-2, 7-3, maybe go into 7-4. Yeah, okay. So we'll have to start chapter 7 next week, and exam should be on Canvas. I had 2 exams. They were very successful for Calc 2 and Pre-Calc 1 on Canvas. Today, tomorrow, and on Sunday, right, always noon to noon, I'm having the algebra exams. So every week there are exams all the way through finals. So we have 2 weeks left of instruction, and then the last week of finals. So we'll get through as much as we can. All right, guys, I'll see you later. Bye. Do the homework.